Well, hello there. This lesson is mostly going to be using features on your graphing calculator. And so the exact features of your specific calculator are things that you need to be familiar with. So I'm not going to speak to any specific type of calculator. But once you know how to use your calculator, most of this is quite quick. In general, we're looking at equations and equation systems, which means multiple equations quite often at once. And when dealing with polynomials, we have degree 0, degree 1, degree 2, degree 3, degree 4. For different types of polynomials, which goes on. And there's fancy names if you want to use quartic instead of degree 4 to feel extra smart. And sometimes we call that the order of the polynomial as well. This is a fourth order, third order, second order, and so on. And let's just get straight to it. And so I have a function here graphed. This is a fourth degree polynomial, a quartic polynomial, 4x squared minus 7x squared minus 2x plus 1. And you can see it here. And I'm calling this p of x, p for polynomial. So first, without graphing or even using some sort of app on our GDC, how can we show that -1 is one of the roots? And remember, a root, same as a 0, as an x-intercept, and different ways of calling the same thing. And so that -1, it sure looks like it's right here, because that looks like it's halfway just by eyeballing it from 0 to -2. But how do I know that's -1 without using some feature on my calculator? Well, one of the key ideas of that is if this really is -1, which it is, our job is to prove it, then that means when x is -1, my y value is 0. And that's true for any function. So in this particular function here, when x is -1, my y value, the output, should be 0. And so a way I can prove it's correct is just to take my polynomial, and I'll write it first in function notation. Instead of having x being x, let's replace or substitute x with -1. If I do this, I get 4 times -1 to the power of 4 minus 7 times -1 squared minus 2 times -1 plus 1. So keep in mind, I'm substituting x with -1, which means I'm putting -1 into the function, and we want to see what comes out. And what comes out is 0. I get 4 take away 7 plus 2 plus 1, which is 0, or you could do that on a scientific calculator. And so notice we put -1 in, that's our x, and 0 comes out, that's our y. That's describing a root or an x-intercept or a 0, whatever you want to call it. So there, we've proven that really is one of the roots. So what are the rest? So there's 2 other x-intercepts, and there's a y-intercept. And so without graphing, but using our GDC, how can we determine the rest? Well, one thing I'll just mention that I think is the easiest is the y-intercept. The y-intercept is when x equals 0. When we put 0 in is what comes out. That's always the case for your y-intercept. And by looking at the equation, I can just see quickly if x equals 0, all these terms become 0, and all I have left is my constant term. So I know the y-intercept is 1. All right, that was nice. What about the rest of my x-intercepts? Well, there's nothing wrong with graphing, and we've learned before how you can quite quickly graph this function on a GDC and then use various features to see the x-intercepts. One feature you want to be familiar with on your GDC is something called a polynomial solver. And there's different ones. For example, in the TI-84, it looks like this. It's PLYSM. Oh, it helps if I can write my letters in the right order. PLYSMLT2 is what it is on mine, which is the polynomial, I guess simultaneous it stands for. I don't know. But there's various features on there where you can literally just type in an equation. You pick the order. For example, on the TI-84, you pick the order. This is an order of 4. And as long as you know how to use the application, it really quickly shows you all the roots or the zeros, the x-intercepts, which we're trying to find here. So all we got to be careful about is that if you notice this equation here, it doesn't have an x cubed term. There's an x to the power of 4, there's power of 2, there's power of 1, there's a power of 0, a constant term. There's no x to the power of 3. So for whatever your application you're using, you want to think about your function as being 4x squared plus 0x, sorry, not 4x squared, 4x to the power of 4 plus 0x cubed minus 7x squared minus 2x plus 1. We want to think about our function being in this form. And then depending on your particular GDC, you'll type in these coefficients of 4, 0, -7, -2, and 1. You'll let it be known that we're looking at a fourth degree or fourth order equation. And you hit a button and it does all the grunt work in the background, and it tells you all the solutions. All that's left now is to look at the solutions and figure out how they connect to our graph. And so with it on my calculator screen, and ideally you've figured it out on your own, there's only two solutions or two x-intercepts I haven't yet labeled. One of them is this right here, which when you look at your solutions, that must be to three significant figures. That must be the 0.265. I've just realized again that there's three x-intercepts I haven't labeled yet. There's this one here, which is my other negative x-intercept, which is approximately to three significant figures, -0.671. And there's this x-intercept over here, which to three significant figures is 1.401. And so the key is just being very familiar with your particular GDC. With a little bit of practice, it's very, very quick. But again, your job is to be familiar with your own. And so ideally, we can kind of take any polynomial of any reasonable degree and find x-intercepts really quickly using that. All right, I have an applied, fairly standard sort of applied question here with quadratics, describing the height of a diver over time as they jump from a diving board into a pool. I want to find how long it takes, how much time passes after the jump before the person enters the water, rounded to two decimal places. And I want to do it two different ways. Once by graphing a system on my GDC, and as well as by using my GDC to solve a polynomial equation. So maybe I'll do the graphing first. So if I want to graph this, I want to graph this equation here. But instead of h of t, I'll probably write y equals -1.2x squared plus 1.4x plus 10. Now, if I want to find where this person enters the water, I want to find when their height above the water equals 0. So the other part of the system I'm graphing is where y equals 0. Well, that's just the x-axis, so I don't really need to graph that. So in terms of using a graphing device, all I really need to do is graph this and find the x-intercept. And when you graph this, you will see there's two x-intercepts, but one of them is before the person jumps. It has a negative value for time. Then so quite quickly, when I graph this, I should find just one x-intercept I care about, and to two decimal places, it's approximately 3.53 seconds. And because we've done similar things before, I don't think I need to go into Desmos or some graphing device to show that. But obviously, you need to be familiar with your own GDC for that. Well, another approach, though, which is no better, no worse, is to realize, again, I'm trying to solve where -1.2x squared plus 1.4x plus 10 equals 0, which means I can think of it as a degree 2 or quadratic equation where I have -1.2x squared plus 1.4x plus 10, and I want it to equal 0. And so my solutions for x are the same as the zeros or the x-intercepts, and it's just like the last question. And I can, in the exact same way I found the x-intercepts for that fourth degree polynomial before, I can find the x-intercepts here. And again, I'll get two of them. One of them I don't need. It's a negative value of, again, -2.36 it'll say. But for this, the context of this question, I don't need. All I need is the positive one, 3.53 seconds. So really, it's a matter of opinion which one you like better. Ideally, you know both. Sometimes looking at the graph is quite helpful. We can see the shape of how a function behaves. Sometimes we don't need that. And so it really just depends what you want. They're both good. Last thing I want to talk about are systems of equations, which I'm sure you've learned about before. And solving a two-variable system of equations, there's lots of algebraic approaches, and it's generally fairly quick. Once we just add an extra variable, we have three variables here, it quickly gets much more tedious. It's not so much difficult to solve a three-variable I gotta learn to speak. I'll try that again. It's not so much difficult to solve a three-variable linear system algebraically as it is just annoying. And those sort of annoying, mundane things are what computers are really good at, or calculators. And so your GDC should have some sort of solver for this. On the TI-84, it's found in the same sort of place as where your polynomial root solver was. It's the next option down, the simultaneous equation solver in which you tell it how many equations there's going to be, how many unknowns there's going to be. And so in this case, I have 3 equations with 3 unknowns, x, y, and z. All you need to do is make sure your equations are written in a sort of standard form, much like my first equation is. And so if I look at my first equation, I don't need to adjust that, but the coefficients I'll need to pay attention to. So I'll have a -1 for the x, plus 1 for the y, minus 3 for the z equals 2. For my other equations, I want to put them in the same form. So if I look at my second equation here, I'm going to leave the 2x where it is, so positive 2x, subtract y, add 2y to both sides, so plus 2y, add z to both sides, or z, whatever you want to say. I got 1z there, and I'll leave the 11 where it's at. And lastly, for the third equation, there is no z variable, so I have just 1x, I have minus 4y, I have 0 z's, and it equals 5. So I just want to get it set up like that. And so what we'll then focus on at this point are the coefficients of x, y, and z. And your GDC should be able to take care of that quite nicely and quite quickly. And again, you want to be familiar with your own specific GDC. Once you have that, though, you type in those coefficients as well as what they equal. Hit a button, and it tells you the solutions to some degree of so many decimals. In this case, I want 3 sig figs, so the x comes to approximately 6.48, the y comes to approximately 0.370, and the z comes to approximately negative 2.70. Just writing it to each of these to 3 significant figures. And again, finding this algebraically would be, because especially these values, these decimals were not nice, clean, whole numbers, this would have been exceedingly tedious to do. And really the graphing calculator makes short work of it. So obviously in a course like this, it's not about just getting these answers. Later on, we need to apply these things, but ideally our GDC can do this sort of work really quite quickly, and we can then focus on more challenging questions that require these sort of solutions.